So as you go to altitude, the power reduces. Now, with the turbocharger, what we do is we pump this one back up here. Or maybe even higher. So as we go to altitude on the ideal cycle, we reduce the exhaust back pressure. If we do that, power increases. If we reduce the exhaust back pressure, power increases, but the inlet pressure is also decreasing, so we are reducing power. And that generally results in a net power loss, particularly at full throttle. You know, when we've got the throttle all the way open, so all the air is going through, the valve has not closed, it's all the way open, all the air is going through the carburetor. But if we can maintain a manifold pressure at sea level and at altitude that are the same, the power at altitude will be greater because of it's working, doesn't have to work as hard against that back pressure. This is one people have a hard time understanding in this course, okay? This is the reason I'm stressing, is that you'll get a manifold pressure and an RPM at a given altitude, and you'll get one power, and you'll go to altitude, and power will be less. You say, wait a minute, no, power goes down with altitude. At full throttle, yes. That's the difference, okay? At full throttle, you can't get any more air through that opening, okay? But if you've got some reduced manifold pressure, you're going to get more power out of the engine, and we'll see that here in a minute. Well, we have a bunch of things affecting the power. We've got friction losses in the engine. We're going to talk more about the friction losses. We have power losses due to the exhaust back pressure. Induction system will have some losses. They will primarily come from either turbulence inside the induction system, or due to the fact that we have to heat that air to take care of the possibility of icing in the system. You can never get those things so they're really closed completely off. So you will always have a temperature rise inside the induction system. If you're doing this in this course, we'll just take the ambient temperature, okay? But if you're doing this for real, you need to place a probe in the induction system after that carburetor heat valve, and use that temperature to determine your power, because there's going to be a temperature rise over the ambient. So there's going to be induction system losses due to that. Well, hey, we like electronic gadgets these days. So we got to have power, electrical power, and so we run an alternator off the engine, and that takes power away from the propeller. Okay, and then due to the fact that we have to cool that thing, we have losses due to the cooling. In fact, on a light airplane, the cooling losses the cooling drag, or the drag to cool the engine, is about 25% of the total. Think about that. You could get rid of that 25%. You can make these things go fast. Just a thought. All right, now here's the real world. here's what's happening, all right? Exhaust back pressure is less, intake pressure, now we've got to subtract this from this. Well, shaft horsepower. On recip engines, you can determine that, with a dynamometer. It's a big round thing you put on the front of the airplane to measure it. One of the troubles with that is that if you actually use a dynamometer on a propeller-driven airplane, number one, it moves the propeller out, and that changes the propeller efficiency, okay? And number two, it's going to affect the drag of the airplane, so it's kind of hard to do. The best thing you can do with a dynamometer is to actually test the engine on the ground with the dynamometer and then take it off and put the propeller back where it belongs. That sort of thing. On turbines, they kind of come with their own, and that's kind of neat because then the horsepower output is just the RPMs times the torque, which you have a meter that tells you the torque. You divide that by 5252 and you've got the shaft horsepower. So turbines driving a propeller are a lot easier to determine the horsepower. You've got pretty much a direct readout in the cockpit, if you do this equation. That's RPM and that's torque. Well, on reciprocating engines, the output torque is a function of the combustion gas pressure. Sorry about that. Somebody wants to give me a free cruise. And we call that the brake mean effective pressure. So if you can measure the pressure in the cylinder when this is all going on, then you can compute the brake horsepower. You measure that, and that's the engine displacement, 0540. So 540 here. RPMs, brake mean effective pressure, whatever it is, divided by 792,000, and you get brake horsepower. Trouble is measuring this. So we do the next best thing. We measure manifold pressure. So essentially this engine is just a pump, okay? So it's just an air pump. And so as a result, we use manifold pressure, and the manifold pressure is the air pressure inside the engine manifold. Okay, after you've been through the carburetor. So what you'll see is manifold pressure, RPM, and temperature used on most engine power charts. And here's one. Now, if you take all these lines, we call this the sea level side. It is the power you would get at sea level. And the engine manufacturer, if you're doing a new program, they can give you a calibrated engine. And what they will give you with that calibrated engine is this sign, this sea level sign. You see all of these lines, if you notice they're kind of coming together, way down here someplace they all come together. Anybody have any idea what that point is? If you were to take the engine and motor it, turn its crankshaft.
And the thrust, it would be the vacuum that would produce?
It's the friction horsepower. The horsepower it would take to overcome the friction of that engine. okay? Way down here someplace, off this chart, all these lines come together at a point. So if you know that and you have a couple of these lines where you can determine that point, you can get all of them. Engine manufacturer will, put the engine on or diamond on her and give you this kind of information. This side, you get through a calculation. We call the left-hand side the sea level side, and all those lines go to the friction horsepower. And we determine through an engine calibration. The right-hand side, we call the altitude side, and we get the RPM lines from this equation. Brake horsepower at altitude is the sea level brake horsepower times sigma, density ratio, sigma, minus 1 minus sigma over 7.55. That's the equation that gets you these lines or the altitude side of the chart. Now, how do we read this thing? Because you're going to have to read it. You've got one in your handout. Okay, if you got your letter, why don't you, if you've got it with you, let's open that thing up to that power chart. And I'm going to give you some numbers, and I want you to tell me what the horsepower is going to be. Let's say we have 2,500 RPM. We have 24 inches of manifold pressure, and we are at 5,000 feet of pressure altitude. Now, okay, let's say, okay, here's 2,500 RPM, 24 inches of manifold pressure. We go up to here to where those two come together on this chart. It's right here, and we come over and it looks like this one's about 182 horsepower. It's not what you're gonna find on that one, I don't think, but what's the consensus of what it is on that side?
A little under,
2,524 inches.
a little under 200.
You're on the wrong side. Yeah, what did you get on the sea level side? Let's do it first.
188.
100, everybody agree, 188?
190.
190?
Oh,
Going once?
yeah, that'd be closer. Yeah. 190.
190, okay? Everybody agree with that? So the sea level side on your chart. All right, now let's go to the altitude. Let's just take that 190, take it across to this axis right here and put a dot right there. Then go to 2,500 RPM and 24 inches of manifold pressure, and I'll be, looky there, it goes right here, or thereabouts, okay? On my chart. Where does it go on yours? What is the horsepower shown there? Do I hear a number? 210? 208. 208, 206. I'm not going to argue about 2 horsepower, okay? Let's say it's I'm gonna say the altitude side, 208. Whoa, wait a minute. Why is it higher at altitude? Same numbers I give you, right, for each one? Just 5 to 10 minutes ago, I was talking about exhaust back pressure, right? That's why it's higher here. There's less exhaust back pressure for that same combination, okay? Now, we're not finished because we want to connect 190 and 208 with a straight line. And don't be ashamed to extend that line beyond the chart. Okay? Connect those two numbers with a straight line. And then, go in at 5,000 feet down here and go straight up until you intersect that line. And that is the horsepower that you are developing at that combination. Okay? Does that make sense? So you connect the 190, I'll just try to do it here, and 208 with a straight line, and then we go in at 5,000, which happens to be, you know, out here. And then we read, just straight back across to whatever that horsepower is. What's the new horsepower at that altitude?
About 208 still. It pretty much lined up with the 5,000 already.
Okay,
Pretty close.
pretty close to 208,
Yeah.
okay? How about that? So, by going to 5,000 feet, with that combination of manifold pressure and RPM, we're drawing almost 20, or we're drawing 18 horsepower more at 5,000 feet than we did at sea level. Due to the fact that, if we go back to that, if I can go back there, if we go back to this chart, it's because of this difference between those two. Oop, going the wrong way here. So that's essentially how we use this chart. Once we get to doing level flight performance, every data point that you get, we're going to have to determine that. Or so we'll use that chart a lot. Now, if you were to see, and I don't know if we've got it on here or not, if you were to see well, guess it's in here. If you were to see a turbocharged engine, these lines would look kind of like this, and then they start down, okay? Why? Because that turbocharger is going to keep the pressure up to a certain altitude. One of the things, if you're testing an airplane with a turbocharged engine, one of the things you have to determine is what we call the critical altitude. That's the altitude where that wastegate for the turbo is completely closed and you can't get any more exhaust through the turbine. And then it starts acting like a normally aspirated engine. But what that will do to this side of the chart is all these lines will be straight until you get to that critical altitude, and then we'll start down. Okay, so we had two, we've got a left-hand side, which is, is determined on the ground. The right-hand side is calculated from that equation I showed you. And so if your engine manufacturer gives you an engine calibration, you can build your own power chart from that. To use at altitude. Again, that right-hand side, those RPM lines are developed off of this equation. There's a third method that you can use that I have used at least once in my career, and that's called the fuel flow method. When you've got an engine, where is the energy coming from that it's developing? Coming from the fuel. So if you can real accurately measure how much fuel you're using, and you know some things about the engine, what its efficiencies are, if you measure the fuel flow, then you can determine the power output. Now, on a turbocharged engine, here's the corrections. Here's what you read off of their chart, okay? Then you put in the temperature correction. By the way, you use this same correction for this part right here, not this part for a normally aspirated engine, like the one you're looking at in your chart there. I prefer to do that. There is a little line down at the bottom of that chart that'll tell you how to correct the temperature. I generally don't use that. I use this equation. I just factor it in, put in my chart horsepower, and then I use standard temperature. This is carburetor air temperature. We don't have a probe in our carburetor on the Saratoga. Maybe we ought to put one, but so we'll replace carburetor air temperature here with outside air temperature or ambient temperature, okay? And then that temperature plus in Celsius, in this case, plus 288.16, and then whatever the standard temperature is for that altitude, and take the square root of that whole thing and multiply it by what we read off the chart, and that will give us the temperature correction. For this, this is the one for the turbocharged engine. This is the exhaust back pressure, the test value that we read, and this is what it should be, the standard. And generally about a 1% increase in horsepower for 2 inches of manifold of mercury, 2 inches of mercury decrease in the exhaust back pressure is about what that works out to be. Okay, if you're trying to determine the critical altitude of a turbocharged engine, you climb into altitude, you get various, essentially at full throttle, and you want to determine where the knee of that curve is. Well, you take temperature values as you're going up, you take manifold pressure and what have you. And so this is the observed manifold pressure that you see as you're going to altitude. And you're reading temperature at the same time. So again, here's our, square root of that equation times the manifold pressure gives you the actual manifold pressure for a given pressure altitude. And then you can determine what the real critical altitude for the chart is. Okay. Guess it's lunchtime. Questions? Everybody knows how to read the power chart now. No problem, everybody will get all of the numbers correct. We'll see. All right. Those pray for